time sliding mode control for the longitudinal aircraft motion. In today's lecture, we'll be covering the mathematical formulation of the control, and also we'll have the MATLAB code to simulate the control algorithm, what we'll be designing for the dynamics. So first, let me define the dynamic model for which we'll be designing the control. The longitudinal motion of an aircraft can be described as theta double dot equal to f theta dot t plus z theta t and ut plus disturbance. So we can write down this equation in compact form for the longitudinal motion. So here basically we are controlling only the pitch angle of the aircraft. Let us define this equation as equation number 1, and where theta of t is the pitch angle to be controlled, and theta dot t is the pitch rate, E of t. Here we are applying only one control input, which is the elevator deflection control input. This is basically the command to the elevator deflection. And if theta dot t is the nonlinear function, or you can say known nonlinear dynamics, and z theta t is the control coefficient gain, we can say. And for this particular case, we can assume z theta of t to be 1 for simplicity in control design. But you can take the full model of the g theta of t, but in this lecture we are taking this as a to be 1 for simplifying the control synthesis. And also the disturbance t of t, this is we assume to be the bounded disturbance, unknown bounded disturbance. The bound is given by dt, which is the magnitude of this, or norm, which is less than the capital D. So capital D is some value, the magnitude of the d of t, maximum value. And our control objective is design the control U of t such that theta of t tracks theta dg t. So this is our control objective. Let us solve this problem using finite time sliding mode control. So here theta is the actual, we can say actual state, and theta desired t is the desired state. So our main aim is we have to design the control E of t, which helps theta to track the theta desired, right? So from these states, we can find the error. So let us define the tracking error as E of t equal to theta t minus theta desired t. So our goal is E of t goes to 0 as t tends to infinity. So this is our control objective. Now we can define the sliding surface based on the error function, because we are trying to define the dynamics into error form, and here E of t can be the state variable. So we are defining the sliding surface in terms of E of t. Okay. So the sliding surface is chosen as S of t equal to E dot t plus lambda E of t. So if you notice this sliding surface, it is very stable function. So here, if you consider E of 0 is some constant k positive value, and if S of t is 0, we can write E dot t plus lambda E of t equal to 0. So E of t we can solve as k into e to the power minus lambda t. So this is basically a stable function, asymptotically stable function. This is how we define the sliding surface, what we have discussed in the earlier lecture. And here, lambda is greater than 0, which is basically a design parameter. And which determines the convergence rate of the trajectory. So if you notice here, in this case, so if you increase the value of lambda, we can reach to the equilibrium very fast, right? So now we'll define the dynamics in terms of the sliding variable. So here let us define this, the equation number 2. And defining, taking time derivative of equation 2, we can write S dot t equal to E double dot t plus lambda E dot t, right? And if you substitute this in place of E double dot t, theta double dot t minus theta double dot theta dj double dot, we can write. So here we can write theta t minus theta dj double dot t, and plus we can write lambda into theta dot t minus theta dot t. We can keep this part as it is, because we have in the dynamics, we have only theta double dot, right? So if you want, you can keep it, or we can write simply as it is. So you can write E dot T. And if you substitute in this equation, the dynamic equation defined by equation 1, theta, which is theta double dot T. So we can substitute here. We can write here f theta dot T plus U of T plus dt minus theta dz double dot T plus lambda E dot T. So here, z theta T, we have taken 1. If you remember, this is we have taken to be 1 here. So that's why the coefficient of U of T is 1 here. So now we'll design the finite time control for this system. So now, as we have discussed in the earlier lecture, we have to design this control U of T. And if you remember, we had two components of U of T. One is the sliding control, another is the switching control, another is the equivalent control. So switching control we define by the signum function, and equivalent control we can define by the functions involved in the dynamics. So if you remember in the from the last lecture, we can write the control U of T can be defined as U of T equal to EQT plus USWT, right? So here U of T you can find, so set S dot equal to 0 in the absence of, why you're taking S dot equal to 0, that is also we have defined. In the absence of in the absence of disturbance, this is basically asymptotically stable function, right? This is already have defined before. So we can write absence of dt, we can write U of U EQT, we can write as minus f theta dot t plus theta dz double dot t minus lambda E dot t. Simply you can write from this equation. So let us define this equation number 3, 4, right? And also the discontinuous term. So the USWT can be expressed in terms of discontinuous term to achieve the finite time convergence. So why you're adding this term, that is also we have defined in the earlier lecture. So we can write USW T, we can add minus K signum S of T, right? So using this to control, okay, there is simple way. If you find difficulty, what you can do is you simply, in place of S dot of T, you can substitute this term, which gives the switching control, and this term, this term, this term, and this term will provide the equivalent control. So this is the simple way you can design the equivalent control and sliding control. And disturbance, anyways, we are making it 0 in when S dot equal to 0. So now the total control we can define as the total control U of T, we can define as U of T equal to U equivalent T plus U switching control. So already we have this expression, we can write minus F theta dot T plus theta dz double dot T minus lambda E dot T. And in place of SU switching control, we can write K SGN S of T. This is the overall control for the equation 1. So now we'll go to the stability analysis. So for stability analysis, we have to define the Lyapunov function in terms of S, because our we have the system, it's defined in terms of S, the steady variable. So here is, so we can define the Lyapunov function as is chosen to be V of t equal to half s squared t. And if you take the time derivative, taking time derivative, we have v dot t equal to half st s dot t, right? Now here we can substitute in place of s dot t as half, sorry, this half will not be there in his. Yeah. So if we can write s of t, so in place of s dot t, we can write, so s dot t, we are having this expression. So now we'll substitute the full expression, what we have here, equation 3. And here we have to consider disturbance also, because we are checking the stability in the presence of disturbance, right? So we can write if theta dot t plus u of t plus dt minus theta dz double dot t plus lambda e dot t. We can write this. And here we can substitute the expression of e of t, which is defined by equation 6 here. So now if you substitute equation 6 in equation 7, we have p dot t equal to s of t f theta dot t plus, it should be minus f theta dot t plus theta dz theta double dot dz t minus lambda e dot t minus k st. So this is what you're having now. So from this, sorry. So from this we can write. So this this one cancel, and we can write from this expression, we can write further. I think I have missed one term here. So here we have another term minus theta double dot t, right? So this term will cancel out. So from this we can write st into dt minus also okay, I have also missed another term here, plus lambda e dot t, because we are substituting the value of u of t here, which is defined by this expression. So it should come here. So again, this both the term would cancel out. This term, this term. Yeah. So finally, we are having, we can write dt minus k HCN ST. Right. And since we have dt, the norm of dt is less than equal to capital T, and also we are assuming this k is greater than d. So this is the condition we are having, and for this condition we can write this less than equal to minus k minus d and norm of s of t. This is the whole process we have done in the earlier lectures. So how we are coming this norm, because if you remember, s of t is gn of s of t, we can write as norm of st, because it is always positive, right? And here we can further, we can simplify this expression, this equation number 8. So equation 8 can be simplified as, we can write v dot t less than equal to minus root 2 k minus t root over vt. So this is in place of st, you can write, because we have defined v of t equal to this expression. So in place of st, we can write root vt, right? So, or we can write minus alpha root vt. So here alpha equal to root 2 k minus t greater than 0. Okay. So here, because it is always greater than 0, because k minus t is greater than 0. So actually, if you remember the last lecture, if we have the expression v dot d in this expression, then we can comment that this is finite time convergence. So we can write the above inequality ensures finite time convergence. So this convergence, because we can write v of t from this above expression. Suppose this equation number 9. From equation 9, we can write v of t less than equal to root v naught minus alpha by 2 t whole square. This easily can compute this expression. And as time proceeds to infinity, so we can say this goes to 0, this term. And we can comment from this expression, we can write st reaches to 0 in finite time, which is defined as tf less than equal to 2 v naught divided by alpha. Okay, this part is going to 0, this part is going to 0, because st is going to 0, and vt is defined in function of st, right? So as time tends to infinity, this part is going to 0, and we are left with this, and from this we can find this expression tf. So now this is basically stability analysis, this part. Our main part is the control, which is defined by equation 6. Now we'll see the MATLAB code, how we can get the finite time convergence for this particular problem. So let's go step by step. This is here actually the MATLAB code for the above problem. So here we have defined the parameters, what we have considered before. So here, if you notice, k is 5 and d is 1, so k minus d always positive. And the initial conditions are here for the different states. And we are simulating this program for 10 seconds, which is 0 to 10 seconds. An initial state vector based on these initial values, we can define the initial state vector like this. And this is the ODE solver, which can find the states. Basically, there are 4 states. We can get the 4 states. And these are the states, how we can extract from Z, because Z has 4 component. We'll have later. This Z has 4 component. And these are the simulation, sorry, plots of the states. And this is the function on which the dynamics is defined. So we have the theta dot E and E dot, and these are our desired values we have defined. And this is the known dynamics, what we have defined in the beginning of the problem. And this is the disturbance we have considered. So we have some sinusoidal disturbance acting on the system. And this is the sliding surface, the same structure what we have considered in the analysis. This is the equivalent contour, and this is the sliding contour, and this is the total contour going to affect the dynamics. This is the theta double dot equation, F plus Z into U plus D. So here also we have considered Z equal to 1. Here we have considered Z equal to 1. And F, this is the F we have defined here. Some nonlinear dynamics for F is considered. And this is the error dynamics. And this is the state derivatives of the different states. And these states are going to the this function. And this function is simulated using the ODE45 solver. And this is the results. So if you notice here, we are getting very fine results for theta of t or E of t. So E of t is also going to 0 and theta of t also going to 0, because our desired objective is 0, 0. So this is how we can design the finite time sliding mode contour for the nonlinear system. Let's stop it here. In the next lecture, we'll have a different model of the longitudinal dynamics and how we can design the sliding mode contour. Finite time sliding mode contour. We'll give the full details. Thank you.